In this mini lecture of the Soils, Slopes, and Streams series, we'll talk about erosion and soil sustainability. Of course, we need to study soils and care about them because of how important they are. They make up the terrestrial surface in which we live, and chemical processes in soils control the availability of rock-derived nutrients such as calcium, magnesium, and phosphorus. Soil properties influence where water goes, how clean or drinkable it is, and how quickly it runs off the land surface. And soils play a critical role in the carbon cycle by sequestering carbon in organic matter and actually drawing down carbon dioxide through some chemical weathering reactions. Here I will use two case studies to highlight the role of humans in soil erosion and discuss the impacts at a local, regional, and global scale. In a prior mini-lecture on soil mass balance, we discussed that the maintenance of soils on slopes depends on a balance between the processes that produce it and that erode it away. We also talked about why this balance isn't really all that surprising in natural systems. But this balance can only be maintained if erosion occurs slow and steady, or in very small magnitude events. This, of course, isn't always the case. We will start with a case study in the loess plateau of China. Loess means wind-blown dust, often specifically glacially sourced. And this landscape, the loess plateau, was built over 2 million years by the deposition of dust from the glaciated Himalayan regions and deserts of interior China and Tibet. This area, over 600,000 kilometers squared, has loesses up to 300 meters thick, and it also played a critical role as a cradle of Chinese civilization. Today, much of the loess plateau is desert-like, deeply eroded in places and poor in vegetation. It looked far different than this in ancient times, as it was a fertile land highly valued for farming, which initially developed over trade routes like the Silk Road. These are reasons it was so important for early civilization. In a few centuries, starting around 200 BCE, the area experienced significant deforestation due to the need for wood as fuel. There was also widespread clearing to make way for agriculture and overgrazing. In the 12th century, fires were even set to keep out Mongol invaders. There were hundreds of years of overuse. The loess plateau experienced significant stress, as you see here, making the landscape drier through desertification and impacting the local economy. In this area, now home to 50 million people, the environmental degradation meant agriculture in the region was less productive, and millions now live in poverty. A project started in the 1990s sought to reverse these changes by revegetation of grasses and trees and land restoration. Here you see a before and after photo of eroded steppes. This is before local citizens undertook the massive effort by hand, seen on the right. Despite this massive campaign, it's impossible to erase the centuries of topsoil loss, surface erosion, and deep incision in the landscape. But it's also pretty amazing to see here how much these efforts did over a few years and what they resulted in. Revegetation adds new carbon to the surface soils, increases fertility, and stabilizes slopes that had eroded over centuries. It also helps to reverse the desertification by keeping water in the ground and in the plants and changing the microclimate. This fairly localized effort resulted in measurable changes to the load of sediment eroded to the Yellow River and also impacted the local agricultural economy. Watch this short video. It's an excerpt from a PBS documentary about this rehabilitation project. If you want to learn more, I've also linked to a longer film called Hope for a Changing Climate. It highlights this rehabilitation and restoration effort in the Loess Plateau and also similar projects in Ethiopia and Rwanda. Our second case study surrounds the Dust Bowl. This was possibly the largest environmental disaster in American history and led to the collapse of the economy in the 1930s in Great American Plains. The Dust Bowl is also why this era is sometimes referred to as the Dirty Thirties. Land giveaways during the Homestead Act of 1862 and follow-up acts resulted in a large flux of settlers to the Great Plains and continued displacement of native communities. Farmers and settlers from the east were inexperienced in agriculture of these drier lands. And thus, many of the farming techniques that were successful elsewhere were not well adapted to these areas. They did have success for a short time as early and late settlers turned up soils with plows, but this resulted in the slow loss of topsoil and reduction of stored carbon. But the rain didn't follow the plow as was expected. Many farms were too isolated for useful irrigation, and native prairies and grasslands that had been there for millennia were destroyed. Then, in 1930, the area experienced a natural drought, exacerbated by overuse and then exposed bare ground. With little to no vegetation and soils overturned by plows exposing bare ground, winds in the dry area began to take away soil, leading to dust storms that eroded some fields and buried others. The return of rains ended the otherwise natural drought, though the devastation and displacement of several million was imprinted on the land. Before the end of the Dust Bowl, under FDR, multiple agencies were created, including the Soil Conservation Service and the Soil Erosion Service, now the NRCS. These were meant to better understand and conserve the soils that were linked to ecosystems and human livelihood. This resulted in education and development of conservation farming techniques like contour plowing and crop rotation, though these were slow to take hold by many for decades, even in this devastated area. We'll expand on the impact of conservation agriculture at a global scale next. Pause the video to learn a bit more about farming techniques and how they influence erosion. We learned in the prior lecture how and why soils can persist over long timescales. They're produced and eroded by the same processes and at the same rates, meaning a soil mass balance. This quote by a pivotal study on global erosion rates stated that the estimated rate of world soil erosion in excess of new soil production is 23 billion tons per year, or about 0.7% loss of the world's soil inventory each year. However, these estimates have gone up as we collect more and more data and as the imprint by humans on erosion in the land surface increases with rising populations and the warming, and in many places, drying climates. It is now estimated that during the last 40 years, nearly 1/3 of the world's arable land has been lost by erosion. This erosion is largely driven by human activities and far exceeds the rate of soil production by natural processes. Let's put this into context. In this graphic, you see erosion rates measured by scientists and geomorphologists across a range of different landscape types. Let's start at the bottom with this category called cratons. These are extremely old areas of Earth that have experienced little change by plate tectonic processes or mountain building, typically assumed stable for over 500 million years. Here we see erosion rates are very slow. Mostly are far less than 1/10 of a millimeter per year. Note this is a logarithmic scale, so these erosion rates have a very, very, very wide range, extending down to only 0.0001 millimeter per year. That is less than 1/2 an inch per billion year. Try to imagine. Move up to the next category. These erosion rates are measured on soil-mantled hill slopes, like we've spoken about a lot. Here, not surprisingly, we find higher erosion rates. These are still probably slower than you might expect. The system erodes at less than a millimeter per year by natural processes, the creep and heave processes that we've discussed on soil-mantled slopes. But the average is less than half of this. These rates also represent the rate at which soils in balance are produced. Next, systems like the European Alps, Himalayas, and steep mountains of New Zealand and Taiwan tend to erode faster than a millimeter per year. These are systems with steep topography and abundant landslides. Many are actively uplifting as tectonic plates collide. And lastly, let's look at the topmost category. These are modern erosion rates in areas with significant human imprint and agricultural land use. And if you're new to this data, it should be disturbing. What this means is that a landscape like this erodes at the same rate as this one. Erosion rates in many agricultural areas far exceed those from the soil-mantled hills and plains they were developed from. Remember, this is a logarithmic axis. This means that soil production and erosion in these areas are far out of balance. Something of serious concern, as we've already seen from the case studies, with respect to their both long and short-term sustainability. Of course, agriculture feeds human society, and importantly, it's not that we farm, but how we farm. There's a wide range of erosion rates off agricultural lands. As seen in the prior case study, farming practices make a big difference in soil conservation. And a major contributor to the Dust Bowl was the inability to adopt appropriate dryland farming practices. While I focused on these rates outlined in red, it's important to also acknowledge these. These are modern erosion rates from areas with conservation agriculture that limit tillage and minimize disturbance, rotate and use cover crops, leave crop residue after harvesting, and keep organic matter in the soil, limit bare soil exposures that are likely to erode away by wind and water, and help to conserve the soil resource. These techniques are increasingly adopted and practiced on modern farms worldwide. Though there's been some resistance, it's increasingly recognized that not only does conservation agriculture have less obvious negative impact on the environment, but that it can also contribute to food security. In the next mini lecture, we'll move to the mountains and hills that are literally at the edge, where processes such as landslides influence landscape evolution and pose hazards to humans.